Okay, so hello everybody. Can you hear me? No. Okay, so first, I'm sorry for the delay, but there was an auction going on, so I thought it would be good to delay the start of the session a few minutes. Okay, my name is Daniel, and today I'm going to talk about an USB host driver fuzzer, which I developed in the last couple of months. Actually, a little short disclaimer. So this is an implementation talk this time. We are still finishing the tests on the software as well as the tests in fuzzing against the host stacks and host drivers. So no exploits are given today. I'm sorry. But still, it can be interesting to see first how USB fuzzing is done and what you can do with it. Okay, let's have a look at the agenda. I'm going to talk a bit about the USB basics, the basic stuff you need to know to understand why one would do host driver fuzzing and what you need to do host driver fuzzing. Then I'm going to talk a little bit about the hardware I'm using. It's called a phase dancer board, produced by a very neighborly neighbor. Also, I'm going to talk about the Dizzy fuzzing toolkit I'm using for the fuzzy input. Then I had to make some additions to the fuzzing framework to get it capable of using USB as an output. And in the end, I will show some examples for actually running USB fuzzing, and then we will discuss a few results we already have made. Okay, so let's start with the basics. Who of you have ever heard about USB? Okay, so yeah, actually it's, where's Sergey? Is Sergey here? No, he's not here. He would tell you USB stands for Universal Serial Bus, but actually it's not a bus, it's a network. And you will see why when you see what goes over the USB cable. Okay, a few basics. So let's start with a history. The development of USB started in 1994. That was the first version, started to be specified. Then it was released in 1996. This was USB standard 1.0. Then shortly after, in 1998, they updated the standard. There was a release 1.1. In 2001, they released an even faster, the super high-speed USB, which is USB release 2.0. And a few years ago, the release version 3.0 was finished and is now widely spread in your hardware. Okay, this USB standard is developed by, or was developed and still is developed by a group of companies. I've just listed the companies who started defining the 1.0 specification. And so the standard is written by a forum, the USB Implementers Forum, or USB if. Is the abbreviation you will find in all the documents covering anything with USB standardization. Okay, there are mainly 3 different versions of USB still used today, which is version 1.1 with 1.5 megabit per second, then version 2 with 480 megabit per second, and the new awesome fast USB 3 with 4 gigabit per second transfer rate. So this talk will only cover USB version 1.1 and 2.0 because the hardware I'm using is only capable of those 2 versions. So the toolkit or the hardware is not able to fuzz specific USB 3 elements, but maybe if the neighbor releases a new board, it will have USB 3 support. We will see. Okay, so to understand the process of USB fuzzing, you need to know a little bit about the USB descriptors. There is the main descriptor, the USB device descriptor, which itself identifies your USB device. There is stuff in like, this device is from a given vendor ID and it has a given product ID. Those two values are used by a host operating system to identify the device. And also in the device descriptor, there is a number of additional configurations you can request from the device. So you also have a configuration descriptor, one or more configuration descriptors. So your device can run in different configurations. Then inside of the configuration descriptor, you have an interface descriptor, which describes the interface you're using. If your device is an, I don't know, external keyboard, for example, you will use a human interface device class in the interface descriptor. And the operating system will automatically know, okay, yeah, I know HID, human interface device, I can do that. I don't need any proprietary driver, let's just load the USB keyboard driver. Okay, there are also some other descriptors like the endpoint descriptor, which describes the direction of the data flow on your USB endpoint and also some capabilities of the endpoint. So also you can request some strings where is, for example, the vendor name embedded or the device's name or the serial number. Okay, this is a short overview how the descriptors are encapsulated in each other. So you first have the device descriptor. In there is a number of configurations, and you got that number of configuration descriptor you can address, and they again have a number of interfaces, and the interfaces again have a number of endpoints. Okay, so on USB enumeration, so if you plug in a device to your notebook, what happens is first the operating system will request a device descriptor, read from the device descriptor the number of possible configurations, and also a field which is called default configuration. Then it will request the default or the selected configuration descriptor. And inside of the configuration descriptor are all the other sub-descriptors embedded. So this is a huge, or can be a huge bunch of data. And once this configuration descriptor is parsed, all the strings are looked up. So inside of the descriptor, there's just a reference, which says like, okay, on this point, there should be a string, but instead of a string, I give you an index, like 5. And if you request a string descriptor with the argument 5, you will get the string I'm referring to. Okay, this can be, as I said, for example, the manufacturer name or the product name or a serial number. So if you sniff on your USB, on your universal serial bus, then you will see something like this. So you can see the host is requesting a device descriptor and the device answers with the device descriptor. Then the host requests a configuration descriptor. Again, the device answers with a configuration descriptor. But now you see the same step again. The only difference on those two descriptor requests is the length of the request. Because in USB protocol, the host, if the host requests a descriptor, the host has to define how long the answer is. If the descriptor, anyways, is too big to fit into the size, the device will just answer with the head of the descriptor. And will also give back the full length of the descriptor so that the host knows, okay, the last answer is incomplete. I need to ask again with a bigger payload size. And afterwards, you can see all the string descriptors are requested. And from the size, you can see those are different answers. So those are all different strings. Okay, another point of USB, especially in this context of fuzzing and you guys, how does it stand with security? What do you think? Is USB or was USB kind of secure in the past? No, you're right. I've just searched for some vulnerabilities from the last year, and there we go. There are some Windows vulnerabilities on parsing USB device descriptors. There was a Linux kernel driver with a buffer overflow in the USB handling code. Also, I found a nice Stack Overflow on Solaris. And there are also user space tools that are vulnerable to attacks from the USB interface. OK, but this isn't surprising, is it? Good. OK, so much for the basics. You know, it's all about the descriptors in the first way. And afterwards, when the driver is loaded, there are some communication channels established. We can also address them. OK, let's talk about the hardware. I'm using some external hardware to do the USB fuzzing. This allows me to send raw USB PBDUs. So I'm not bound to any API my operating system is exposing to me, but I can just give raw data to the hardware, and the hardware sends it out on USB. The hardware I'm using, the phase dancer, consists of first an USB to UART chip, which is the host connect. So my notebook running the Fuzzer is connecting via this USB interface. Then the UART interface is connected to an MSP microcontroller, and the MSP microcontroller again is connected to an Maxim USB controller. And this USB controller is the target connect, so this is where I connect the host I want to fuzz. And yeah, that's it. It's not a lot of stuff. It looks like this. So you can see this is the host connect. You got the USB serial to UART connect, chip, then you got the microcontroller, and this is the Maxim USB controller, which connects to the target again. OK, if you talk to Travis, he sends out the PCBs. So if you're interested, you can get them for a very low cost, just for shipping cost, I guess. And if you solder it, it will look like this. So it just got two mini USB and the stuff on the PCB. OK, it's the phase dancer is controlled from PC host. And the PC uses a Python library to access the hardware and to deliver content to the target USB chip. So all code you're going to write is in Python, which is really nice because developing and debugging on an embedded system is always painful and costs a lot of time. So it's way faster and easier for me to write the fuzzing code in Python and run it on a notebook instead of putting all those code on a microcontroller. Also, the USB library, the Python library that comes with phase dancer, implements some basic layers of the USB protocol. So you don't even have to go all the way down to the packet exchange and all that stuff. So this is here. You can just use it. You have to implement a little bit of code. You have to implement your USB device and the interface, but that's it. All the other stuff is already there. You just run it, and the enumeration can happen. OK, you will find the source code and hardware stuff on SourceForge. Take a look at it. It's a really nice project. So this is just a screenshot of the USB protocol layer. So you see down here is the layer 1, which is the link layer, and the whole link layer up to here, where the green border is implemented in the Maxim hardware chip. So this is way out of our focus. We don't have to care about getting data on the cable. We just see the raw packet data units. Then this upper layer, which is orange, I guess, is implemented in the phase dancer USB library. So all you have to do is to implement your device code and all the functions you want to run on top of USB. Okay. So the next point is Dizzy Fuzzing Toolkit. This is the fuzzer I'm using to generate all the fuzzy payloads. And I've got a short definition of fuzzing here. I'm sure most of you will know it because it's the first mention of fuzzing in academia. So I just skip this. We're already short on time. You can read it later. So Dizzy is a Python-based fuzzing toolkit. The first release was in 2011. It got a quite simple packet definition syntax, which is also Python. And it does stateless fuzzing as well as stateful fuzzing. Here's a link to the latest release. You can just download it and play around with. Ah, Sergey, there you are. Hello. I quoted you before.
Alrighty.
Yes. I said when Sergey would be here, he would say USB is not a bus, it's a network.
Indeed.
Okay. So this is the smallest packet definition you could think of. So it contains just a variable called name. And afterwards, you have two lists. One is called objects, and one is called functions. In this example, it's completely empty. This is just the bare skeleton you need. The objects array contains the single fields of the packet. So if you look at your Wireshark packet dissector, you will see packets are split into different fields. Let's say a version field, a type field, and a length field. And once you know your packet is structured like this, you can also put those three fields in the object array. Now I said, OK, there is a length field. So somewhere in the generation of the packet, a length has to be calculated and put in the right place. So this stuff goes into the function arrays, where you say, after generating the packet, you need to call some functions on it and run some calculations. OK, available objects are, I will go in there a little deeper on the next slide, but these are just the objects you're able to put in there, and also there are some functions you can use. They're all described in the README file in a more detailed way, but I will give you a short introduction anyhow. So let's take this packet description file. This is my typical example. That's why it's called example. And then you see again the objects list and the functions list. This is the packet I just mentioned before with a type field, a length field, and a value field. And that's exactly what this says. OK, we got three fields here. One is called type. I could have called it whatever I want. Then this field has a static length of 8 bits. Also, it has a default value of 0. And when I start the fuzzing process, I want this field to be mutated in every possible state, so from 0, 0 to FF. And this is why I put a full in here, so this field should be fully fuzzed. Okay, so it's almost the same for the next field, but this is called length and got the default value of 6. And the last field now is a value field. It has no static length, so it can, the length of the field can vary. The default value is the string fuzz, so it has, in default, a length of 4 bytes. But while iterating over the field, it's not just counted upwards from 0 to FF like the other fields, but in this place in the packet there is for each iteration a given fuzz string put in, like your SQL injection string or some code execution strings, or just pounds or something like that. Those strings are defined in a text file and just read line by line. So, and then in the end, there is also a length function, which is called after the packet is generated in data. And what this says is, please put into the field length the length of all fields from type to value. So the length of all those 3 fields is calculated and put into this destination field. OK, this is really easy. This just contains fields and length. This is what you will see in most of your packet descriptions, as most packages carry a length somewhere. This now is a real-world example. This is just an ARP reply. So you see all the fields of your ARP package. In this case, there is no function because ARP has only static length fields. And I got some default values in here. So this is a absolutely functional script. You can do ARP fuzzing with this. Just to show you a real-world example. Then there are even more objects you can use. For example, the random object. This one just has a name and a length. And in each iteration, the whole length will be filled with random data. Then there is a list object, which again takes a name, takes a default value, and takes a path to a file on your system. And in each iteration, one of the lines of the file will be put in. Then this is just a normal field again, as we saw in the first example. And on the end, there is a link object, which just got a name and a source. And the content of this object, the content and the length, will be the same as the content and the length of the source object. So in this case, I'm just copying the random generated data up here, down there again. OK, then there is also padding. I don't want to go through this in detail, but you can also pad data. OK, so far for the packet descriptions. With packet descriptions, you can only do stateless fuzzing. So you just go through one packet and send it out millions of times with with small iterations in the packet data. But what if you think about stateful fuzzing? If you have to log in somewhere before you can address the target you want to fuzz, then you need some kind of multi-step function. You first need to authorize yourself, go through the login procedure with valid data, of course. It doesn't make sense to start fuzzing here because you want to be logged in and fuzz something afterwards. So I figured out kind of an interaction concept. This is represented just by a series of packets, or in this case, packet description files. Those packets are sent out in order. So I say my first packet is like the first visit of the page. This one is sent out, then the answer data is read back. The second packet is like my authentication data with username and password and stuff like that. And the answer is, let's say, an authentication token. I send out this packet and read the answer back. And then I need to put this authentication token in my next packet, which is the actual fuzzing payload, because now I'm authorized. I'm at the step I can begin fuzzing. But I still need to copy the authentication data. And this can also be done in the interactions, so I can copy parts of an answer and use it in further transmissions. To describe an interaction, I use a similar description file. So you got a name again, and you got some objects, and you got functions. Objects in this place are this object, so you give them a name, and you just reference a packet description file. So in this example, the tool will just send out the first packet, will read in between, discard the red data, and send out the second packet. Okay, this is just some made-up example. Let's go to a more real-world example. This is the authentication I just talked about. So you have your first visit of the page, which is a packet description, let's say HTTP GET. You can just describe an HTTP GET in your packet description file and send it out. So afterwards, data is read back, but nothing happens at this step. Then your authentication data is sent out. So this contains your username and your password. Afterwards, data is read back. And in this case, because I got a copy function referencing the second read step, data is copied. To be more precise, the data from the answer from offset 0x10 to 0x20 is extracted from the answer of your server and is transferred into the field named auth in the next dis. So we need a field named auth in this packet description file, and this field is automatically filled each time you read back your authentication cookie. And then the last one, the command, is where I want to put my fuzzing payloads. So this file will be iterated with each step through the interaction. So these 3 packets are sent out each time I'm going through one iteration. So I'm visiting first, I'm authenticating, then I'm sending the default packet. Then I'm mutating this packet, so I somewhere change a value of the field I'm currently fuzzing. Then I'm going through the whole process again. I'm sending the first packet, I'm authenticating, and I send the mutated command packet, and so on and so on. So I'm only mutating the last packet in this case because I just want to fuzz the authenticated command. Okay, so far for Dizzy and Dizzy's packet descriptions. Now I had to add some USB additions to Dizzy to get it work against USB. And I had to modify the main program and add 2 new output types. So you can now, instead of just raw Ethernet, TCP, UDP, and SCTP, you can now also select the USB descriptor or the USB endpoint as an output. So also I've added some Dizzy to face dancer glue, which is implemented in the USB.py. And this mainly implements the device and the USB interface required by the face dancer Python library to emulate a USB device. And also there is a class implemented which is used by Dizzy to start, stop, or control the USB thread delivering your payloads. Okay, that were the coding part. Anyway, if you're interested in the code, just have a look at it. It's on the website I showed you before. If you have any questions in place of the code, just drop me an email. I'm always happy to answer questions about code. Okay, but now let's see how this would work in a whole process. So, okay, I know all this. You implemented a lot of new stuff. You can do USB now, but how do I do it? Okay, so first you have to choose your target. So there are many targets on USB, so you could address the device descriptor. You could address, for example, the configuration descriptor or some string descriptors or something in the extended descriptors. Or you could just target one endpoint. So endpoints are the connections where actually data is transmitted. In the example, I choose just one of the descriptors for an easy start example. Okay, descriptor fuzzing targets the USB stack of your host operating system, where the endpoint fuzzing targets the USB driver attached to your USB device. So this driver might either be from the operating system vendor or from a third party. And yeah, this is the interesting part. All those crappy USB drivers delivered by third parties running inside of your kernel, those are the interesting ones. Okay, but now I want to fuzz some USB device or the driver for some USB device, but actually I don't own the device. How do I get the descriptors I need? I need to see a real descriptor before I can start splitting it up into fields and put it into a packet description and start fuzzing of this description. I first need to know how it looks originally. So this is, while we are currently setting up an online collection of USB device descriptors and configuration descriptor. I registered the domain usbdescriptors.com. There is no content yet, but there will be a database with USB descriptors. You can contribute to the collection either by submitting just the output of an LSUSB, which almost every Linux user could do. But you can also, in the case of a more complicated descriptor, just deliver the descriptor raw, just in hex. But this would require additional tools. OK, so once you choose your device or your driver you want to address, and you somehow manage to get to an original, your hands on an original descriptor, so you now got the descriptor. The next step is you need some hardware. You need an host PC to run the fuzzing tool. You need the famous phase dancer board. You need 2 USB cables to connect both. And of course, you need some target. Then you need a bit of software, which means you need a Python interpreter and the DZ framework on the host. You need the USB device file, which in this case is the USB descriptor you either got from a real device or got from the database online. And then you need your actual fuzzing payload, which is the packet description file. OK, so let's go through it step by step. You choose to take the descriptor from a real from some real hardware. So you need to attach the hardware to your system. You need to find on which port it is connected and then get the output of the LSUSB. Then I got a kind of ugly Perl script who tries to pass the LSUSB output and get it into something DZ can use with, which is then your USB descriptor file. The script is not perfect. It's not working for very complex descriptors. So those you should take raw from the device. OK, the second step would be to create or modify your payload, your fuzzing payload. In this case, I choose the configuration descriptor, packet description. This file already comes with DZ, so I wrote this descriptor once. You can just use it or modify it to your needs. For example, if you set every field to full fuzzing, the fuzzing will never end. Those are way too much iterations, too much mutations to go through. So you have to decide, okay, I'm gonna target this field on this run and maybe the other two fields on the next run. Okay, so once you got your payload ready, you just need to attach the hardware, so put the phase sensor board in between your host and the target, and then just run the fuzzing. In this case, this is a DZ command for starting USB descriptor fuzzing, and you're using this USB descriptor file to emulate the device. Also, you're going to target the configuration descriptor, not the device descriptor, but the configuration descriptor, and here goes your payload. So once you launch this command, it will take a while. Because USB takes some time to connect itself, to be recognized by the host that there is a new device attached, to be enumerated from the host. Some systems do it a couple of times, other operating systems just do it once. So it also depends on your target how long this process will take. And then again, these are, in my tests I came about 4 to 5 seconds per try, which is really, really long. Normally I'm fuzzing with something like a delay of 1/10 of a second between the packets. Now I'm talking about 4 to 5 seconds per iteration. So the fuzzing process will be slow. Good, and the last and final step would be just to attach Wireshark to your USB monitor and watch the process happening. You don't have to watch it while it's running, but you should record it in the case something crashes, that you can see what happened, what packet actually got sent out and how the host responded and on which step of your maybe multi-step setup the host crashed. Okay, to sniff USB on Windows, USB PCAP is needed. You will find it here. Okay, so this was a real-world example. That's exactly the methodology we're currently using to run USB fuzzing. But as I said, it's really, really slow. It's running for a long, long time. And so we don't have any spectacular results by now. But we got some results. Those are mainly from the development phase. While I was writing the code and testing if the code is working, some stuff happened. So yeah, as I said, we didn't perform wide-scale fuzzing or a wide scale of vulnerability analysis on USB devices. Still, I triggered some unexpected behavior. For example, a host or USB stack crashes. This happens on Windows 7 and Linux, on both systems in a recent version. So 3.10 is not the latest kernel, but it's not an old one. Also, I think the Windows 7 was nearly fully patched. I'm not sure if there was the update bubble down there or not. It was while developing, but those were recent systems. And yeah, they crashed. Also, I saw software crashing running on the target. So Skype, for example. Wherever Skype is listening to your USB interface. Then I also tried to attack a virtualized system. So in this case, I used VMware to virtualize the host and then just attached phase sensor to this virtual machine. So I got 2 cables from my host connecting to the phase sensor. And on VMware, for example, after a few iterations, I got this little error. So VMware wasn't able to connect the device null to the virtual machine. And afterwards, I couldn't attach any USB device at all to the virtual machine, so I somehow crashed the virtual USB stack, I guess. Okay, I didn't investigate those crashes in depth because it was just while I'm testing the implementation, and implementation in this case was the main prio. But no worries, we will investigate those crashes in the future. We're currently running a set of USB fuzzing instances against a series of targets, but as I said, they will run for a long time. Okay, now with the conclusions. First, you have to see, in the past, USB fuzzing was really expensive to do because you need specialized hardware, you need a big USB debugging box or whatever. But by now, there is low-cost hardware, really cheap hardware, with which you can actually do USB fuzzing and test your USB implementations or the implementation of your operating system. So from my perspective, would say expect a bunch of new USB vulnerabilities to show up in the future. Because as more people start looking at this topic, there will be more findings. Okay, so that's it for now. Thank you for your time. And are there any questions? Monsieur?
Hi, I was just wondering what the scale of your fuzzing is on USB. Like, are you guys running like 10 hosts, 100, 1,000?
No, currently it's more like 3 host machines and 3 target machines. So I'm targeting Windows 7, current Linux, and the 2000 and what is it? The new server 2012? Yeah, 2012, I guess. So the desktop Windows, the server Windows, and the Linux box. Okay. Any more questions? We still got some time. No? Okay. Well,
the testing where you had an issue with the USB host virtual driver, did you note whether that remained if you brought up a new instance of virtual host? Was it hypervisor-wide or? Yes,
it was hypervisor-wide. So there is one process which is responsible for the USB virtualization. So the parts of the software which takes care to attach the physical device to the virtual machine. And this is just a daemon running on your hypervisor. And yeah, apparently this daemon, it didn't crash, so it was still running, but it doesn't do anything at all. Okay. So.
Okay, so then thank you very much. Now time for technical.
Yeah, thank you.